Hello and good day to you. So I'm going to try and do a quick video on linear regression and residuals, trying to impart to you two ideas. One is the ability to use residuals to assess your general linear model for whether it's appropriate for your use, and that comes mostly from your first graph here. I'm using a data set from Kaggle again. Don't you look, just love Kaggle. This is predict breathe. It's got the peak difference, period, and oxygen per litre, and we're trying to show relation of period and oxygen per litre. As you can see, it looks fairly linear with some breakaway data out there. And what we're showing here with residuals is to show basically a single point on your residual graph is an actual value observation minus your predicted value. So the more it goes up here, the more inaccurate your model is. And as you can see, being 10 out for predicting period, probably actually quite bad but a lot of it is very close to the zero. So whether you sort of say that's very accurate or not is up to you. You can see that the quantiles show the relationship within the data in terms of normal distribution. What you can see is if you saw a perfect line along this, you'd know it's normally distributed. When you see these wiggles on the end, and this is extreme to be honest, you're saying it's not normally distributed, and I'd say there's probably data skewed, but I do have graphs to prove that. And then you have standardized residuals, which is the square root of the residuals, and that just makes a nice little compact graph. And leverage is interesting and something I need to go into more. But the further it goes along this graph, the higher the Cook D value. And it's basically because the way R and most, well, I think all calculated linear regressions is ordinary least squares. So it chooses the line of best fit that minimizes the square roots between the different values on its graph, and can do that for multiple dimensions. So this is why you can use linear regression and put in multiple different values, and you'll also see ordinary least squares pop up in equations for training neural networks. It's something that I want to get my head properly around the math and build something that can use it properly. I mean, it's a pretty useful formula to have under your belt. But if I was to then move on and try and show you what more nonlinear data looks like, you can see here that what's happened is we put a nice graph, a linear regression, a nice line from ordinary least squares, and if it was working perfectly, everything would be lined up along the zero axis, and it's just not. It just goes off in a massive curve. And actually, I think, one of the reasons I chose this data is it's meant to be quadratic data. So if you see major curves in your residuals like this, the data is quadratic, and you're going to have an interesting investigation on your hands to get to the root cause and calculate it. If you see, that it just peaks up at the end, or that it sort of, crosses the axis like this, you could say that it's non-linear, but that's probably a bit easier because it's easier to square root values and times values by other values, put values to powers, put values to logarithmic values, as a way of dealing with nonlinear algebra than it is, in my mind at least. I mean, I haven't really done much with quadratic equations, so I don't know how hard it is to to calculate this properly. Again, you've got your quantiles that will show you distribution of data, so you can see this is less non-normally distributed. You can sort of see some wiggles, but it's not huge compared to the other one. You've got the same again, and you can see the leverage, and you can see the idea that this goes a bit higher in its Cook-Dees value, so you might have some more values going on. And what you can use, so what I'm going to show you is if I build a value that combines this. So I've just seen that previous residual and decided that I need to have some more data. So I've now combined period and peaks difference to predict oxygen per litre, and that's lessened it. It's not just taking it away entirely, but it is. There's more values on the 0 point. You can see, you know, it's still not normally distributed, but you can also see it's better with on that thing. Same again for leverage, though. You know, you can see the axis is about the same, and that probably lets in what you can then do with residuals. Having looked at this, you can start with looking for, does one number predict another, and you can start to see is if there is this nice linear relationship, you can go, yeah, that probably is causing that, or that at least has some sort of relationship going. If it's skewed like that, you might say that if it was curved like that, you could then go, well, there's non-linear linearity going here. It might be a quadratic equation if it's really curved like it was, and it lets you just have some insight into what causes what in your data. You can go around looking at numbers and looking to see if there's a relationship going on. You can plot these residuals and share them with managers and team members to get them thinking. And the final point I'm going to make is you can use the predictions function and you give it a level. So I want 95% confidence, and this will give me a predictions for my data. So I'll print it out, but this is where it becomes quite useful. Bear with me when I get to the top. So you've got your fit, which is what the actual assessment is. The lower is the lower given some randomity or random behavior, and the upper is the sort of upper expected. So you've got a rough guess of deviation, variance in your data using this linear regression model, and then you can also do the same again, but that was a confidence, and you can use a prediction, and a prediction will give you in absolute terms. So give you an idea. So you can see here the range is massively increased, but it's giving you an idea of actually how much chaos there is in your data. You can actually give an idea of, given this what's happened before, here's the middle of what we're going to say, here's the lower value it might come in as, and here's the upper, and that's produced very simply by R, done using ordinary least squares. You don't have to just use continuous data. If you it takes a little bit of manipulating and munging of the data, but if you had say, and I've done it elsewhere, where I've had a list of customers, and you're not obviously going to put customer 1 is what value 1, customer value is value 2. Don't do that. What you're going to do is you're going to take customer A, B, C, D, and add them into your data as binary values of 0, 1, So it's 1 where that customer is involved and 0 when they're not. And that can then be inputted into your general linear model. And what's quite interesting is if you see multiple lines on your residuals, or if you see like groupings in it, like where you might go, well, I've got a bunch of residuals there and I've got a bunch of residuals down here. There's a good thing to start to question unless it just looks completely random, which, don't get me wrong, that will probably happen some point. And I don't want you to spend ages trying to figure out a fix. But one thing to question is, do you have 2 variables? Do you have multivariability? Do you need to sort of say different, this is my base continuous value I'm using for prediction, but they behave slightly differently, and I need a offset based on, is it this customer or that customer? And that's one way to think about it. And hopefully you can go away and use this in your R and use this in your general linear regressions. I hope this has been of use to you. Have a good night and a good day. Bye.